And you go on from there. So let me make this a little more concrete. When kids first start to learn to speak, they learn some basic words, right? And they don't look them up in the dictionary. It's experience, right? You connect what you hear with what you see, and okay, that must be a tree. Same thing with the numbers, right? We're counting things. 0 is the number you use when there's nothing there, right? 1, 2, 3. 3 rocks. Is that the same as 3 birds, right? And do 3 rocks kill 3 birds, or is there better optimization of that? But these are the numbers, right? Piano came up with this sort of, a way to build them concretely. So he said 0 is a number, and then he said we'll just have this operation called next. So whatever's next after 0, we'll call it 1. Whatever's next after 1, we'll call it 2. I mean, these are just the numbers we all use, we all know, we all love, all love, some of us love, okay. And then one other thing, which is kind of reasonable, it says if you have a small collection of these things, these numbers, then one of them is the smallest. Well, okay, big deal. Seems inconsequential, but that's the system. And you can put them together in ways that don't make sense. Careful, the soon equals 7 minus. These don't really have any meaning. Some do. My homework ate my dog has meaning. This could either be a kid who just accidentally transposed the words. Could be the class clown. He's trying to get a rise out of his friends. Could also be a teacher that asks the students to bring in wild animals. I don't know. But you can make some sense out of it. There's many meanings maybe you could come up with. 17x is 4 is similar. You have many meanings. This could be true, could be false. You don't know what x is. Maybe this is how you define x. Anyway, so you can make sense of these and then ask later whether or not they're true or false, or when they're true or false, things like that. Here's some things that are true. The world is round. This was discovered recently. I don't know if you've been reading the ASU news, but some other things. Here's a neat one, so get the bags ready. Here I'm just going to add up a bunch of odd numbers. The first bunch of odd numbers. Okay? N of them. Think of your favorite number n like 7. So I'm going to add up the first 7 numbers, and I'm supposed to get 7 squared. So is that true or false? Apparently it is. These are things that you can verify. The world is round was first verified by measurement, right? And nobody believed these people for a long time. They're only scientists, after all. Does that sound familiar? But later on, it's a little bit easier to, we got pictures, okay? So that's a little easier. This is also verifiable. We call it a proof. You can look at one way of doing this. The first 4 numbers are centered around the number 4. So that's kind of their average. So 4 numbers with average 4 adds up to 4 times 4. 4 squared. So this is, you could do it with 5, same thing. 5 numbers are all centered around 5. So the answer, when you add them together, should be 5 squared. This actually was a method purportedly invented by Gauss when he was 5. So that'll put us in our place. Here's one that's false. Red is gray and yellow white. And you decide which is right and which is an illusion. Who knows this? Moody Blues? Nobody knows? Ah, there we go. Moody Blues fan in the back. Okay, so. Sorry. Knights in White Satin. It's great classic. Should have brought a clip. Here's another one that's false. You can take certain numbers and square them and see if 2 squares add up to another square. This one turns out to be false, and again, you can verify this simply. If n is 1, then n squared is 1 squared. That's 1. Then 2 squared is 4. 3 squared is 9. And this certainly doesn't add up. 1 and 4 is not 9. So these are things that are verifiably false, right? True. Here's a different way to add up 2 squares that do make a square. It's a different sort of pattern. It's an example of, you might know the Pythagorean theorem. It says if you've got a right triangle, then these 2 legs, when you square them and add them together, gives you the square of the hypotenuse, right? And so this is an example of a solution to this system with whole numbers, which is kind of a curiosity, but maybe not much more than that. It's kind of fun to think about. Some people a long time ago thought about, what if you added up cubes? A cubed plus B cubed is C cubed. Well, let's try it. They couldn't find any. In fact, Fermat asked this question about 350 years ago, and it was only answered about 10 years ago. It took a long time. And I would venture a guess to say that maybe 80% of all mathematics that exists today is due to people trying to solve this silly little puzzle. Now, you can debate with me whether 80 is the right number, but a lot. A lot. It turns out to be true. So what are we doing here? Are we inventing theorems or discovering truths about these numbers? I mean, this is sort of a question about, are you a Platonist or not? The Platonic thinking is that we're discovering truths. These are numbers. We didn't invent them. They're just sitting there. And whatever you say about them is true or false because that's how they behave. Okay? On the other hand, you might ask about, say, War and Peace. Did Tolstoy discover or invent War and Peace? Maybe we should show, vote here. Should we do border voting or should we do? Because literally, this is just a big book. Okay, who cares how big it is? It's just a sequence of symbols. Anybody could have written these symbols down. I'm not saying it's likely or unlikely. Nobody really wanted to until maybe after Napoleon, but certainly they still existed before that. All right? So maybe that's an argument that War and Peace existed before Tolstoy. That's kind of the argument you're making when you're saying these numbers existed and you're discovering these theorems about them, these truths. Other people think that maybe we're just doing a little bit of both, that you're discovering truths about a system you invented to approximate, I hate to use the word reality, but whatever that means. I'll let you sort of come to your own conclusions about this. And let me add another one, infinitely many primes. Prime numbers, if you remember, these are things that don't have any divisors. Like 6 is 2 times 3. It's not prime, but 7 isn't one thing times another in whole numbers. So that's prime. And Euclid knew, again, that there were infinitely many of them. He had a nice argument to say that. More recently, 1850, more recently, a couple weeks ago, Chebyshev showed that something stronger, that pick a number like 2, double it, 4, there's a prime number, 3 in between. Double 4 is 8, 5 is a prime number in between. You keep doubling, and there's always a prime, pick any number, 100. And between 100 and 200, there's a prime number there. Okay? So it's a kind of way almost to start accounting for how many percentage-wise are there. This was reproven by Erdős in the 30s, and they had this nice little rhyme that goes with it. Chebyshev said it, and I'll say it again. There's always a prime between n and 2n. See if you wake up with that one tomorrow. Start it's always a prime between n and 2n. Why would you reprove things? I mean, if you already know they're true. Well, developing methods, finding really the reason for these things is a nice exercise. But twin primes is something also Euclid was very interested in. These are numbers that are prime, that are 2 apart, like 11 and 13, 17 and 19, twin primes. What's the next one? 41 and 43. 42 snuck right in between there, but that's irrelevant. But anyway, these are twin primes, and they get harder to find. 71 and 73 might be the next twin prime. They're harder to find. Nobody knows. Again, this is 2,300 years ago. What have we been doing? We don't know if there are infinitely many of these or not. So is this a question like parallelism that you can have a choice, answer it one way, answer it another, depends on where you're living? Nebraska might say yes.